Okay, we're going to finish up the basics of circular motion and centripetal force before we go on to some examples. Now, we talked about centripetal force. Another term you're probably familiar with from last year is centripetal acceleration. And this is the acceleration of an object due to a centripetal force. Of an object due to a centripetal force. The equation for centripetal acceleration, as you remember from last year, is AC equals v squared, the speed squared, divided by the radius. Now, this equation can be derived. I'm going to skip the derivation. It's not particularly important for you guys. When you think of the word acceleration, you have to be very careful here because a lot of people will think this means the object is either speeding up or slowing down. And when an object has centripetal acceleration, that does not necessarily mean that it is speeding up or slowing down. Does not necessarily mean object is speeding up or slowing down. What it does mean, on the other hand, is it means an object is changing direction. Okay, because remember, there's three different ways that an object can accelerate. It can speed up, slow down, or change direction. Centripetal acceleration, when an object has a measurable centripetal acceleration, that doesn't necessarily mean that it is speeding up or slowing down, but it must mean that the object is changing direction. As a matter of fact, when the object is not speeding up or slowing down, when it's moving at a constant speed, that is referred to as uniform circular motion. Circular motion in which speed remains constant. That's what uniform circular motion is. Okay? So you could have a situation, if something is not moving in uniform circular motion, where an object is moving in a circle and is speeding up or slowing down, but it still has a measurable centripetal acceleration because it's changing direction. But that's not going to happen all the time. There are instances where the object is neither speeding up nor slowing down. It is moving at a constant speed, but it still has a centripetal acceleration because the direction, if it's moving in a circle, is always changing. Very quickly, let's just go over the direction of vectors for an object in circular motion. We've kind of already done this, but let's just rehash it anyways. Okay, so if I were to give you a bunch of positions here, 1, 2, 3, 4, and 5, and what I'm going to ask for is not a free body diagram. Instead, it's simply a little, I like to call it like a circular motion diagram. What direction are the three main vectors of circular motion pointing in? What direction is the velocity pointing in? What direction is the centripetal force pointing in? What direction is the centripetal acceleration pointing in? So, for object number 1, remember, centripetal force always points towards the center of the circle. Oh, let's say that this object is moving counterclockwise. So we have FC pointing towards the center of the circle. If it's moving counterclockwise at point 1, that means it's going this way, so that would be a velocity vector like this. And the question is, what is the direction of AC? Well, remember that when we have a centripetal force, that's just like a net force. Matter of fact, Newton's second law, and we'll get to this in a second, for circular motion, is Fc equals MAC, with the C's meaning centripetal or circular, and that's your reminder that we're dealing with a circle here. Since Fc is equal to MAC, whatever direction Fc is in, since Fc is a vector and AC is a vector, whatever direction Fc is in, AC must be in that direction as well. So for number 1, we have Fc and AC pointing down towards the center of the circle, V pointing tangent to the circle. Okay, that's another way. Remember, the velocity always points tangent to the circle. It points in the direction the object is moving in at that instant. The centripetal force points toward the center of the circle, so does the centripetal acceleration. This isn't a free body diagram because these are not all forces, okay? There's no axis. I'm not labeling the object. This is just a quick little diagram to remind you of what direction these vectors are all in. At point number 2, let's see, center of the circle is to the right, so that means we must have FC to the right. AC is also to the right. And then the velocity is perpendicular to that, tangent to the circle. Let's see, it's moving counterclockwise, so that would be down here. At point number 3, we have FC and AC pointing up, and the velocity being to the right. At point number 4, we have the velocity pointing up, FC and AC pointing in. And at point number 5, which isn't one of these kind of cardinal points around the circle, we have the velocity pointing kind of up and to the left, because at that point the object is moving up and to the left. And we have FC pointing down and to the left, because that's the direction towards the center of the circle. And that's also the direction for AC. Okay, so there you go. Those are the directions of the velocity, centripetal force, and centripetal acceleration all around the circle. FC and AC always point in towards the center. Velocity points tangent in whatever direction the object is moving at that time. Let's go back to Newton's second law for circular motion. What we're going to do here is kind of expand this out and derive a formula for what happens if you're not told how fast the object is moving and you need to find the centripetal force. From up here, we know that AC equals V squared over R, so let's talk very briefly. How could we plug this into this equation? Well, I would then have FC equals M times V squared over R. I could write that as this, M V squared over R. If you're a little shaky with your algebra, just realize that this M is really like it's over 1, so I could think of it as M over 1 times V squared over R, and then just follow rules for multiplying two fractions together. Now, here's what I was just talking about. What if you aren't given V? What if you're not given the velocity and you're still asked to find the centripetal force? You're usually given the mass, you're usually given the radius, but sometimes you're not given V. In that case, you're usually given some other information. Let me show you what you could do with that. Here's an object moving around a circle. Okay, so we got an object right here. It's moving around like this. And this is the radius of that circle, right? Let's have, hypothetically, how far does the object move if it moves once around the circle, if it makes one complete lap around the circle? If you said, well, that's the circumference of the circle, then you're exactly right. The circumference of the circle is basically it is the perimeter. And if you have an object that moves once around the outside, the perimeter of that circle, it has traveled the distance of one circumference. So an object in circular motion makes one loop or circumference, and let's say it takes a certain amount of time, t. Since the length of one loop is the circumference c, which is equal to 2 pi r, look what we have here. We know the circumference. That's really the distance that this travels. The circumference is a measurement of distance. The circumference is how far the object travels in a time t. So, notice that we have a distance divided by a time that can give us the speed. V equals d over t I could replace with v equals c over t, which is really 2 pi times the radius over t, since c is the circumference. And since this is the speed of the object, if it is in uniform circular motion, the speed doesn't change, we can take this expression for speed and plug it in for v up here. So it's going to get a little messy. I'm going to separate out the m and the r, so this equals m over r times v squared, times this thing squared. 2 pi r over t squared. So that's fc equals m over r times, let's see, we got squared everything in here, 4 pi squared r squared over t. I look and see if I know I can just combine these because that's how we multiply fractions. I look and see if I can cancel anything out. Looks like I can cancel out one set of these r's. And what I'm left with is FC equals 4 pi squared r m, oh dear, I forgot to square the t, over t squared. That is an equivalent expression for FC, and that will come in handy if you're ever not told what the speed is. So I would practice doing this derivation a few times, okay, until you've got it down. It's not too hard. There's two jumps that you have to make. The first is plugging in the equation for AC into FC equals MAC. The second is realizing how you can figure out the velocity if you're not told it, if you're just given the radius and the time. I would practice doing this, literally writing this derivation out a few times so that you're comfortable with it and can do it very, very quickly. What we're going to come to next are some examples of how to use what we've learned here in circular motion problems.